Hello everyone. So today I figured I'd start talking about digital logic a little bit and put a bit of a pause on my FPGA series, because I figured it would be nice to do something involved with the basics as well of digital logic. So I'll be linking this presentation in the description below. And I'm also going to be using this book as well as other small sources. Digital Design Principles and Practices 4th edition. I think there is a newer version, but this is just the one I have. So in this presentation, we're going to be talking about digital logic gates. Okay. So introduction. So a logic gate is an elementary building block of a digital circuit. Most logic gates have two inputs and one output. At any given moment, every turnable is in one of the two binary conditions, low or high, represented by different voltage levels, either 3.3 volts or 5 volts. The logic state of a turnable can and generally does change over time as the circuit processes data. Basic logic gates. So the first gate I want to talk about is the simplest one, the NOT gate. So the output here is the inverse of the input. If the input is high, the output is low, and vice versa. And here you can see this truth table. Input 0, output 1, and vice versa. And this is just the Boolean expression for the NOT gate. Next we have the AND gate. The output is high, 1, only if all inputs are high, 1. Otherwise, the output is low and is expressed as either Z equals AB or Z equals A dot B. Here is the symbol, and here's the truth table for the AND gate. The OR gate next. The output is high if at least one input is high. Otherwise, the output is low. And the Boolean expression is Z equal to AB. Here you can see the symbol, and here you can see the truth table. The NAND gate is the opposite of an AND gate. The output is low only if all inputs are 1. It's the inverse of an AND gate. So this is the symbol. It's an AND gate with a bubble. This is the Boolean expression A dot B bar. It can also be expressed as AB prime. So you can see all the outputs are all 1 except when both inputs are true. The NOR gate, the opposite of an OR gate. The output is high only if all inputs are low. It is the inverse of an OR gate. This is the symbol. It's an OR gate with a bubble. This is the truth table. And this is the Boolean expression A or B prime. The exclusive OR gate, or the XOR gate. The output is high if the inputs are different. The output is low if the inputs are the same. This is the symbol. It's an OR with also an extra line here. And this is the Boolean expression for it. It's a cross in a circle. And this is the truth table. So you see it's only high when either input is different. The XNOR gate, the inverse of exclusive OR gate. The output is high if the inputs are the same. The output is low if the inputs are different. It is the inverse of an XOR gate. You can see the symbol. It's an XOR gate with a dot, with a bubble. And this is the truth table. So in the conclusion, digital logic gates are fundamental components that enable the complex operations of modern digital technology. By combining these basic gates, engineers can create intricate circuits capable of performing everything from simple arithmetic to highly complex data processing. Understanding their behavior and truth tables is the first step in comprehending the digital world. So I want to make this as part of a series. At some point too, I want to start talking about Verilog and maybe VHDL2. So in the next video, I want to start talking about Boolean algebra. Thank you very much for listening.